Performance of Numpy Array versus Python list over 1D matrix vector. I want to calculate pi, which summarizes several labels in a specific class, total number of labels in the Gaussian mixture model. tr_y is a pandas data frame. (1,000 rows times 1 column). Then I try to compare two approaches. The first one is using list. The second approach is using Numpy Array. Updated approach if it converts Numpy to list using toList is much faster than the two previous approaches. Source of the last approach. So using lists is faster than using Numpy Array. I have searched for this, and I find that Numpy has to wrap the returned object with a Python type, for example, numpy.float64 or numpy.int64 in this case, which takes time if you're iterating item by item 1. Further proof of this is demonstrated when iterating. We see that we're alternating between two separate ids while iterating over the array. This means that Python's memory allocator and garbage collector work overtime to create new objects and then free them. A list doesn't have this memory allocator/garbage collector overhead. The objects in the list already exist as Python objects, and they'll still exist after iteration, so neither plays any role in the iteration over a list. My search concludes that if we need to work on multidimensional matrices or do some vectorization, we have to use the Numpy Array faster and take less memory. Is that true? Another thing that I want to calculate is the memory consumption for both the Numpy Array and list. Still, I find that sys.sizeof is not reliable and gives us the size of pointers array and header of the container, which there is more and more consideration. Is there any reliable method to calculate the memory consumption? Another investigation that when I convert Numpy Array to list I convert it to row matrix which is uploaded into L1 cache at once rather than call vector which makes a lot of misses inside L1 cache. Source. So what if we use a vector in Fortran order?
TL, drive. Use np.sum like this. Testing. Now let's do some experiments. We will use the following setup. We use a larger dataset to see whether the methods scale well to larger inputs. Here we will have a dataset with 1 million rows. We will try a couple of different methods and see how they perform. The worst performer is 1.91s plus or minus 42.1 millisecond per loop, mean plus or minus std.dev. of 7 runs, 1 loop each. The next option is on average 14 times faster. 132 milliseconds plus or minus 2.14 milliseconds per loop, mean plus or minus std.dev. of 7 runs, 10 loops each. After that we get a 1.6 times increase with 79.3 milliseconds plus or minus 796 microseconds per loop, mean plus or minus std.dev. of 7 runs, 10 loops each. None of these methods however are optimized with Numpy. They use Numpy arrays but are bogged down by Python sum. If we use the optimized Numpy version we get 1.36 milliseconds plus or minus 6.7 microseconds per loop, mean plus or minus std.dev. Of 7 runs, 1000 loops each. This operation was on average 58 times faster than our previous best. This is more like the power of Numpy that we were promised. By using np.sum instead of Python standard sum, we are able to do the same operation about 1,400 times faster, 1.9s versus 1.4 milliseconds. Closing notes. Since Pandas series are built on Numpy arrays, the following code gives very similar performance to our optimal setup. 1.83 milliseconds plus or minus 39.6 microseconds per loop, mean plus or minus std.dev. Of 7 runs, 100 loops each. Unless optimizing your code is essential, I would personally go for this option as it is the clearest to read without losing much performance.